we need to know how the dipole moment oscillates, which means we need to know what's the motion of the electrons, of the negative charge. We need to solve for r. And we actually have an equation of motion here. So this is the equation of motion for those negative charges. This was sort of like a spring force. This is a damping force, the mass times the damping constant times the velocity. This was a driving force, and that's ma. So that's what we need to solve. So let's see how we're going to solve that. It looks a lot like the driven oscillator, the driven damped oscillator. So the way we solve it is we guess. R. Let's make that very clear that's an R. R. We're going to guess an oscillating solution. If it's a driven oscillator, if it's being driven at omega, we're going to make a guess that it's going to oscillate at omega. R naught e to the minus j omega t. And we're going to keep things complex. And next, you plug it in. All right, so minus kr would be minus k, that's kind of the effective spring constant, r naught e to the minus j omega t, and minus m gamma dr dt. So if we take dr dt, we're pulling out a minus j omega when we take a derivative. So that's going to become plus j, so this is an imaginary term, m mass of the electron, gamma, omega, and then e to the minus r naught e to the minus j omega t. A lot of terms, j, me, gamma, omega, r naught. And then minus the charge on the electron minus e naught. This is the driving term, you don't put r in it. E to the minus j omega t equals mass of the electron, me. And then two derivatives of r, so that's going to be two negatives is going to make a positive, but then two j's is going to make a negative one. So minus omega squared r naught. So let's see, here's the minus, here's omega squared, here's r naught, e to the minus j omega t. So we plugged in our guess to the equation of motion, and what does the equation of motion say? It says, well, we can cancel this, e to the minus j omega t. It's all oscillating together. And that's pretty much all it says. Let's see, what else can we cancel? Yes, nothing else. That's all we can cancel. So then we just solve it. We say, well, what does this mean, r? What is the motion r? It's this, and this was going to tell us r naught. Right? This is, we already know, we're oscillating at this is the frequency we're oscillating at. We know what that is. We really just need to know what is the amplitude we're going to get. Kind of like with a driven oscillator. So we say r naught, and I'll kind of do this in one step. You would just pull r naught out of these terms, get them all on one side, bring this over here, that over there, and then divide. And that would leave you with a positive e naught. That was the driving force, charge times field. And in the bottom, that would leave this part, me omega squared. Yeah, this would be positive. So this would be down here, me omega squared. And then the next term, this term is positive, j. And let's see, we got me gamma omega, and we're solving for r naught. All right, it's okay so far. And then there's this term, minus k. We're pulling out the r naught. Minus k minus pretty k. There we go, minus a pretty capital K. So this, for now, is our answer. We know that if an oscillating electric field oscillating at omega hits the material, its negative electronic charge is going to move with position like this. It's going to oscillate in time also at omega, the same as the drive frequency. And the key is this tells us the amplitude. It depends on how hard you drive. It depends on the charge. Of course, that's just negative E. It depends on the mass of the electron and the frequency you drive at and the spring constant, just like a driven oscillator.